All right, thank you. So yeah, I'd like to go ahead and start off with the acknowledgments and thank Krell and CSGF. It's been great to be able to work on things that I find interesting, and I think it had a big part of me getting a job at Oak Ridge as well, which I greatly enjoyed. So the title isn't exactly what was in the book. I've had some recent things that I wanted to talk about more within my graduate work, but the whole gist is trying to find an efficient way of integrating the atmospheric dynamical equations for climate models. And so some of the constraints that we need from science, if you take a look at the IPCC, the Intergovernmental Panel on Climate Change, we need a lot of throughput. We're running a ton of scenarios. We need multiple ensembles of each scenario to make sure we know what we have confidence in, at least from model variability. And generally, the community says we need it at 5 simulated years per day. That's about 2,000 times faster than real time. So the problem with an implicit method for the global climate models is you need a lot of work per node to get the efficiency to scale it to 100,000 cores. And the problem with that is those problem sizes don't finish in 5 simulated years per day. So currently, I would love to see an implicit method actually scale out to give us the throughput we need. Eventually, the time step's going to kill us, but for now, we get more science out of time-explicit methods. And it's good for parallel communication. You can strong scale the entire machine if you need to. And it's not so good for the time step, so that's the main problem. My graduate work has mainly been these time-explicit methods, just increasing the time step, decreasing the parallel communication as much as possible to get an efficient method. So design choices you can make in this direction from the algorithmic point of view. You want a fully discrete method. That means you only have one stage of communication per time step, instead of, say, a multi-stage method like Runge-Kutta or an implicit method that has to iterate in order to get the solution in time. And to do a fully discrete method, we have to translate spatial information into temporal information. And what I mean by this is a characteristics-based method where you compute Riemann invariants and you track them over a trajectory. The trajectory is where you translate spatial into temporal. So you trace it upwind over time to where it came from, and you sample at that spatial point. That's the translation there. And that's actually the majority of my graduate work. You can get very large time steps and keep stability. I had it go into a time step 3 times the typical explicit CFL limit. And it has a lot of advantages because you're not communicating. And in fact, it worked pretty well on GPUs. I was getting 25% peak on the GPUs with that algorithm. So there's a lot of advantages to it. But going into multiple dimensions is a nasty problem. You end up tracing a Mach cone coming out from the point source, and it's not intractable, but maybe it's not the best next step for the model. And so I like a method called Eider. I'm not entirely sure what it stands for, arbitrary derivative Riemann problem, something like that. And it uses the PDE itself to get time derivatives out of the spatial derivatives. And you use those time derivatives to step forward in time with the Taylor series. Another choice that we could make is multiple moments per cell. The reconstruction stencil is smaller when you use more moments. And in fact, at the limit, you can get an entirely local scheme. You don't actually communicate with your neighbors to get a reconstruction within the cell. That would be a Galerkin scheme like Spectral Element, which you heard from Judy this morning, and discontinuous Galerkin. And generally, it's more accurate than grid refinement. If you use more local information instead of reconstructed information, it's going to be more accurate. The problem is, usually adding more cells will restrict your time step. And the overall thing that I've heard it touched on, but it hasn't really been mentioned here, is you want more flops. You want more flops in your schemes. It runs better on these vectorized GPU cores. You want to flood the thing with computation if you can add accuracy to your solution by increasing the flops or decreasing data movement. If the increase in flops is either of those, you've probably won. It takes a lot of flops to actually give you a decrease in computation if you've decreased data movement. So the current state of the art, you heard a little bit about it this morning. It's called Spectral Element. And when you think of that, just think of finite element discretization, but the basis functions are local. This is an entirely local scheme. It is multi-moment. It's on the cube sphere grid, which you take a cube and you project it out to a sphere. You get a quasi-uniform resolution. It's got a lot of nice properties. It's non-orthogonal. That's the main downside, but there's a lot. It's fairly easy to deal with. You have a Runge-Kutta integrator in time. They've actually made it past the leapfrog now. The new code uses Runge-Kutta 3. And it runs at 5 simulated years per day at a 14-kilometer mesh, which for the climate community is unheard of. This is truly state-of-the-art. On 90,000 cores is about how many we run it on. That's 93 million unique model points. And the maximum stable time step by linear analysis at this point is 21 seconds, but we use 10 seconds because with a model that's not limited by some sort of non-oscillatory interpolation, you usually can't go right at the stability limit. But before, 93 million is not actually that many points, but we do it in about 5.5 milliseconds per time step. So that's the main novelty of the method. Unfortunately, the time step, usually you have your linear scaling with grid spacing. You cut the grid spacing in half, the time step cuts in half. That's normal, but as you increase the number of modes, p, it goes almost quadratically by linear analysis. That's the main problem with the Galerkin method, is the time step will kill you eventually. So I was reading a study recently, and they use a Hermite Wino that's weighted essentially non-oscillatory to limit the modes of a discontinuous Galerkin method. And they implemented 2 methods. The first one was a finite volume method where you evolve the mean and the derivative. And the other one was the DG method limited by this. You use the derivatives of the Hermite interpolation to replace the derivatives of DG when you need to. But I noticed the finite volume method had a 3 times larger time step than the DG method for the same order of accuracy, and the accuracy was similar or better in a lot of cases than the DG was, and I just asked myself, why did the paper focus on DG? Is this not a competitive scheme in its own right? So that's where I'm going here. If you take an Eider method, we're going to use the generic conservation law. We have a vector of variables we're conserving U, and then we have fluxes in 2 dimensions and a source term. Consider this shallow water equations or something like that. You discretize it in space and time. You just integrate it over a space-time block, and these hat symbols here mean time average, and the bar means a spatial average. So you're going to change the cell mean U for the new time step based on fluxes through the interfaces and the body source term. It's fairly intuitive. Flux in minus flux out gives you the change in the concentration. And to get time averages, which is the fully discrete part, you take one step. The Cauchy-Kovalevsky procedure, that's a mouthful. At each integration point, you form a Taylor series in time, and to get the time derivatives, these du dt here, you use the PDE itself. So if you take the original PDE, you apply the chain rule, and you take the flux Jacobian, you actually get a time derivative from your spatial derivatives. And if you want higher and higher order time derivatives, you just take derivatives of the PDE itself. It's a complicated procedure. Usually I use Maple just to export the code directly. It's very rare to actually do this by hand. You'd probably make a mistake. Multi-moment we get by evolving higher order moments instead of reconstructing them. And so really, I just differentiate the PDE itself. You draw the spatial derivative inside of the time derivatives, and you have something that looks exactly like the original PDE. And so you discretize over a time and space block. You have the exact same finite volume discretization for the higher order moments. Just the fluxes are derivatives of the original fluxes. And that, again, I use Maple to export because that's going to be a pain to do by hand. There's a lot of terms in there, chain rules and derivative product rules. So it uses the same machinery as the original moments, but now we have a local scheme. There's absolutely no communication when you reconstruct your cell. So this has the same locality as spectral element, but the novelty I'll get to in a second. But to get the time derivatives, we use the same Eider technology. So you don't actually step forward in time like Runge-Kutta. You build your Taylor series using the spatial moments that you have already within your cell. So everything's entirely local for one step. So you cut out the Runge-Kutta communications, because every stage in the Runge-Kutta, you're actually communicating data in the parallel machine. You reduce the Eider expense. I don't have time to get into this. I will answer a question if you're curious, but this Cauchy-Kovalevsky procedure is notoriously expensive. And so instead of doing it at every integration point, I just do it once at the cell center and do a space-time Taylor polynomial. You just sample the space-time Taylor polynomial. So you get rid of a lot of the expense. The scheme, you have multiple moments, just like spectral element or DG is spatially local, but the time step does not degrade as you increase the number of moments. And so that's the novelty of this. The CFL remains unity as you increase the number of moments per cell. So it's most similar to a modal DG with a Taylor basis, if you're familiar with that scheme. And you just evolve the value of the first, second derivative. And it's applicable to any mesh. So if you want a triangular mesh, if you want any curvilinear mesh, it'll work just fine with those because all the information is local. You can integrate over the round of the cell with any Taylor basis without any problem. And the Hermite-Wiener limiters apply just to this scheme as they do to a DG scheme. You can limit the modes as you need to. But if you look at the computational aspects, you're decreasing the communication and you're increasing the resolution as you add more modes. So those are both very good. And you don't increase the time step, which is better than your typical finite element method. So increasing the computation is clearly a good thing in this case because it is more expensive than DG, but not that much so. And if you look at the amount of communication that you're decreasing, over a Runge-Kutta DG scheme, you actually, if you go out to 8 moments, you have 70 times less communication as you go from one step to another. So it does pay off as you add more and more moments, even though you have the computation there. So just to give a couple of examples in one dimension, this is still being developed in 2 dimensions. There's a lot of coding debugging to be done there, but the magenta line here is the derivative. And this is Berger's equation. You initialize it with a 1-period sine wave, and you just let it go, and it forms a shock. You can see the points along the shock here. It's a nice sharp front. And the point here is this was limited with a Hermite-Wiener limiter. So even the derivative doesn't have oscillations, which is nice to see. Here we have a strong negative value, but it's bounded to maybe negative 20 or negative 50. So this just proves that the Hermite-Wiener limiter is actually working. And the other question that really we need to know before this would ever become viable is accuracy. So to orient with this plot, this was a 1-period sine wave linear advection using 25 cells, and you do it for 4 revolutions. And this is, on the bottom here is the number of moments. So we're adding modes. This is P refinement, and this is the error, a log plot of the error. So a straight line in this would actually be spectral convergence, exponential convergence. The dashed lines is the DG scheme, and something curious about the DG scheme is as you decrease the time step, it gets more accurate. So the red dashed line is the maximum stable CFL that you could use, and you hit some breaking point where the accuracy no longer decreases. That's due to the time discretization. And using a quadratic scaling of the time step, so it cuts down quadratically with P refinement, or cubically with P refinement is what the purple and blue lines are. And you notice you don't actually get full spectral convergence as you increase the number of moments. That's because of the time discretization. Because the Eider scheme actually has nth order accuracy in time, you're refining the time discretization with the spatial. And this accuracy gets better as you go closer to a CFL of unity. So the closer you actually get to a CFL of 1, the more accurate it becomes. And this actually has super exponential convergence for the linear problem. I'm sure if you went to a real life problem, it would not do that. But it just shows you can get the accuracy that you want. You can get a time step that can be up to 70 times larger for that less communication. And it might actually pan out to be a better discretization. If we're getting an 8th degree, 14-kilometer resolution for CAM right now, if we were to increase the time step, you might actually get down to something like a 5-kilometer resolution, which would resolve the regional scale features a lot better. But with that, I'll take any questions.